All right, so we're coming up on the end of our first day of the Probabilistic Programming Conference. Our last speaker is Feras Saad from MIT, who will be talking about Bayesian synthesis. Sorry, I'm distracted. Shall I just give you a hand? Great. So Feras will be talking about Bayesian synthesis of probabilistic programs for automated modeling.
All right, great. Thank you for the introduction, and thank you to the organizers. I'd like to mention that what I'm presenting today is joint work with Marco Cosimano-Tanner, Ulrich Scheichler, Martin Renard, and Vikash Mansinga. We're talking about automatic data modeling as Bayesian synthesis of probabilistic programs. We'll start with an outline. So first we'll motivate the talk, and then give an example of how we synthesize probabilistic programs for time series data in the Venture probabilistic programming language. And thirdly, we'll talk a little bit about the probabilistic programming formulation of structure discovery. So recently in the probabilistic machine learning literature, there's been emerging trends for specifying richly structured composite probabilistic models over symbolic domains. As an example, Roger Gross and his collaborators in 2012 defined what are known as these matrix decomposition models, where the idea is you have matrices which are random, so they have either Gaussian entries or multinomial entries or Bernoulli entries, and you have rules for composing these matrices. So for example, you can take sums of them, you can exponentiate them, you can take transposes and products. And what Roger showed was, using these primitives and using these composition rules, you can rederive a lot of existing models in the machine learning literature, things like low-rank approximations and random walks and clustering models. In a very similar spirit, Duvigneau and Lloyd, in a series of papers, worked on a system which was called the automated statistician, or ABCD. And the idea is that you have primitives, which are these time series motifs, things like squared exponential kernels or linear kernels or periodicity. And then you can define rules for composing these, such as taking their products and their sums or change points in between them. And using the primitives and the compositions, you can describe a lot of time series structures that appear in the natural world. So one very natural question that arises from these model classes is, can we learn probabilistic model structures using Bayesian inference? So the vast majority of existing techniques are based on greedy search and score heuristics. And what they result in is a single most likely or a single highest scoring model. And they tend to be quite hard to customize the search procedure and hard to implement the structure discovery algorithm. Whereby with an approach based on the Bayesian paradigm, we could hope to obtain posterior uncertainty over the structures that might exist, encode some of the prior knowledge that we have through these composition rule probabilities. And with regards to learning, we can reuse a toolbox of existing methods that people today have been talking about in probabilistic programming systems. And that brings us to the second point is, can we use probabilistic programming to both implement and formalize the learning problem? And the proposal here is to say that we're going to take a model family, which is either a matrix decomposition model or a time series model, and think of that as a domain-specific language. We're going to take model structures and think of them as probabilistic programs in that DSL. And we're going to treat learning model structures as a form of probabilistic program synthesis. So on your left-hand side, we're seeing sort of the statistical interpretation of these different terminologies. And on the right-hand side, you're seeing how we're thinking of those in terms of probabilistic programming terminologies. All right, so the first part we're going to talk about implementing, and then the second part we'll talk a little bit about formalizing. So walk through an example of time series structure discovery as Bayesian synthesis in Venture, otherwise known as ABCD, or automatic Bayesian covariance discovery. So life starts off with an observed data set. So there's some time series. On the x-axis is time. On the y-axis is passenger volume between 1948 and 1960. So we load up this time series in Venture. And what we do as a second step is we're sampling a set of programs from the prior. So here what I'm showing is one particular program that was sampled from this prior over DSL expressions that describe the covariance structure. And then what happens is we have our initial guess. We run Bayesian synthesis, which is going through these different structures to find ones that are approximately sampled from the posterior. And one thing we might want to do is obtain forecasts from those learned models. So the question is, are these predictions accurate? And when you compare them against other baseline methods which require no hand tuning, the answer is yes, right? I mean, compared to Facebook profit algorithm or just a squared exponential kernel or ARIMA, these models can perform very accurate predictions based on patterns in the data. And numerically, you can do this on a broader set of data sets, and you get the pattern that predictions can be more uniform by learning structure as opposed to using general algorithms. Another thing you might want to do other than prediction is quantifying uncertainty about properties that exist in the data. So Bayesian synthesis gives us an ensemble of programs from the approximate posterior. You could imagine throwing those into a little text processor, which is just walking over the synthesized programs to tell you what are the various probabilities that particular structures exist in real-world time series. So for example, in the call center time series, it's very clear that there's all sorts of things happening, like a linear trend, a change point around 1973, there's periodicity, whereby another time series, for example, radio sales, there's very low probability that there's any linearity or change points there. So one question is, why do we formalize this problem, or why do we think of it as a synthesis in a DSL as opposed to general purpose probabilistic programming languages? So researchers have worked on synthesis in general PPLs, but what we've found is that having a high-level DSL gives us a simple and constrained program space where it's easy to write a program and easy to validate that the program will actually run. Whereby arbitrary code is complicated and it's hard to write a prior, and who knows whether what I generate in this example is even a covariance kernel, or whether it will compile, or whether the syntax is correct. It can be very challenging to do synthesis in general PPLs. So we'll walk very briefly through the internals of how this thing works. So one key step is specifying a prior over the DSL code, and this happens in roughly the way you'd expect, right? So there's a probabilistic context-free grammar with various non-terminal symbols and terminal symbols, and their production rule probabilities. And on the right-hand side, you're just seeing how we implemented this probabilistic context-free grammar in Venture. The second step is, now that I have this, particular DSL expression, you need to interpret that to give me a Venture executable that inference can target. And so the interpreter is a very simple thing which goes through the DSL and produces a Venture object that you can observe data against or compute likelihoods against and do synthesis against. And then the final part of this is how exactly do we run inference? So this baseline technique is based on Metropolis Hastings, and there's a recent paper in PLDI which goes into a lot of detail on Venture's inference machinery and how you can actually use programmable inference to perhaps do more interesting things than resimulation MH. All right, so that was first part of the talk, which was an example of implementing a synthesis system in Venture. The second part is, why do we want to treat model discovery as synthesis? So one of the early hypotheses in probabilistic programming, which we used to talk a lot about during the PAML DARPA program, was reducing implementation complexity. So what I'm showing here is a table made by Alexei Radul, who's in the back there, comparing the lines of code between Bayesian synthesis and the ABCD system, just a baseline system that Lloyd and his collaborators created. And even if you take this as a ballpark estimate, you can roughly get the general sense that with probabilistic programming, you can get very interesting workflows, but concise and effective. For end users to do sort of interesting things without having to write very complicated pipelines. I think there's a second question, which is, I showed this diagram, which was saying on the left is sort of the statistics world, on the right is the probabilistic programming world. But is it enough to just write a prior over DSL expressions? I think if you're listening closely to Dan Roy's talk, reasoning about probabilistic programs can be very subtle. Right, so Ackerman, Freer, and Roy showed that you can have a computable prior and a computable likelihood, but the posterior may not be computable. And we would expect that these kind of issues will arise if we're going to be formal about Bayesian synthesis of probabilistic programs. And they do. Right, they do. So things that we have to think about if you're going to sit down and think formally of Bayesian synthesis is whether the prior is well defined, whether the likelihood of the data is finite, does the posterior even exist, does the inference algorithm converge to the posterior? And in order to answer those questions, we need to reuse ideas from the programming languages world. So I won't get too deep into the PL side of the talk, but roughly what we do is we think of the DSL, the DSL as being the language of a particular context-free grammar, and we assign a pair of denotational semantics to each expression in the language. So there's a semantic function called the prior, which maps any expression to its prior probability, and the likelihood, which maps an expression in a particular data set to a non-negative number representing the likelihood of that. And sort of heuristically, you can think of the prior as the probability of a model structure, and the likelihood is the probability of data given that structure. And so sufficient conditions, maybe not necessary. Whether these are necessary conditions, I think, is an interesting question, but sufficient ones are for the prior to be normalized, right? The sum over all expressions needs to sum to unity. The likelihood should also be a proper likelihood function, and the likelihood should be bounded in most cases. And if these conditions exist, they're sufficient to say that the posterior exists. Whether it's computable or not is a separate question, but at least it exists as a particular target of Bayesian inference. All right, so let's take a look at this prior, and formally that's a sum over a countable set of strings, if you're uncomfortable with what's this sum over expressions in a language. And it turns out that verifying whether your prior is normalized is checking whether the sampler for the DSL expression halts. All right, so that sounds like a problem, right? And just to show you that it's not an arcane problem or some mysterious opaque problem that I just conceived or some magical construction, this can show up in a very simple probabilistic program. So on the left-hand side, I'm showing you a PCFG, which is a normalized prior. And on the right-hand side, I'm showing you one that's not normalized. The one on the left halts with probability 1. The one on the right has a particular execution path with non-zero probability that doesn't halt. And the difference between these two is a very small choice in how we decided to write the program. And I was very sad when I wrote the right program and got stack overflows or had very other strange or erratic behavior, or sometimes I couldn't even know what was going on. So these are not just conceptual, but actually practical considerations. So the question is, do I need to solve the halting problem to define a prior over my DSL expressions? And the answer is, if you want to sit down and write arbitrary priors over expressions in a language, then the answer is yes. But is all hope lost? And there the answer, thankfully, is no. So one option, which Ulrich talked about today in his earlier talk, which is how we approach this question for Bayesian synthesis for tabular data, is by using a finite language. Right? You don't necessarily need an infinite language which can generate arbitrarily long strings. A second option is to use a carefully constructed probabilistic context-free grammar. And for that, this is sort of a key insight for me at least, was some very early work by Booth and Thompson in 1973, who showed how to solve the halting problem for a PCFG. So a PCFG is a sufficiently simple probabilistic program, actually, where you can solve the halting problem using a static analysis, which I'll show you how to do. It takes 3 slides. So the first thing is, this is the PCFG that we wrote for the prior over DSL expressions for the time series example. The first step is you translate the PCFG to Chomsky normal form, and you just annotate the probabilities of each rule. I hope you can see them down the left. And then what you do is you check the spectral radius of the expectation matrix of the PCFG. Right? So this is just some matrix that's derived from the CNF representation, and the spectral radius is the modulus of the largest eigenvalue. And if that is between -1 and 1, the program halts. All right. So the implication here is that we've taken this very hard problem, which is figure out whether it halts, and at least for PCFG priors, which can describe the matrix decomposition models or can describe the time series models and any other models that we can hope to write, there's actually a solution to figuring out whether what I wrote is a valid program, and it's actually not that hard to implement, which is what we did. Other things that we've been doing, I won't dwell too much on these because we're in the statistics track, not the PL one, but we started to think about what are the formal semantics of the prior of a PCFG, and there's sort of ways that you can describe these operationally or denotationally and showing that these agree. You can also describe the likelihood semantics of a particular program, and those are just described recursively of the likelihood of a particular composite expression from the DSL breaks down into the primitive components. And we've even gone a step further and thought about, all right, now we've wrote semantics for the prior and for the likelihood. What are the semantics for inference? And some of the things that we've been working on with help from Marco is writing inference semantics for Metropolis Hastings and actually showing, for the case of synthesis with a DSL prior specified by a probabilistic context-free grammar, the resimulation MH algorithm is actually convergent to the posterior. So it's aperiodic, it's positive recurrent, and it has the other key properties that are essential for convergence. And I'll highlight that having a PL formulation is what allows us to think of model discovery or probabilistic model discovery, which is typically seen rather informally in the machine learning literature, and treated actually quite formally as a PL problem. And one can imagine writing these semantics from LaTeX and porting them into a system like Coq and doing verification for different things that you want to check about your inference program. So I'll end a little bit early because people are probably tired. So the summary is what we've done is sort of formalized model discoveries as a Bayesian synthesis. And we've showed that it's practical to implement this using a sufficiently expressive probabilistic programming language. In some of our work, which I didn't present here in too much detail, we've shown that the approach is theoretically well-founded and established the conditions for the inference problem to be well-defined and for the synthesis procedure to converge to the correct posterior. And sort of the higher level goal is to explore more deeply this bridge between PL theory on the one hand and Bayesian model discovery on the other hand. And I think if we want to think of Bayesian model, or we want to use Bayesian model discovery in our probabilistic programming systems, then this bridge is actually a very important one for the community to be thinking about. And lots of people in this room, who you'll hear from tomorrow, are actually doing some very interesting work on that front. And here, this is a part of that work for Bayesian model discovery. So that's all I have. I'll be happy to take any questions from the audience. Thank you. Yes? So this particular code is not yet available, but it will be at a near stage. Yeah. Any other questions?
I think I have a question if nobody else does. So when you have this kind of sampling problem where you're trying to sample from a PCFG, right, you can, of course, run Metropolis Hastings and then maybe show that if you draw kind of infinite samples, eventually it converges to the target distribution. What is your experience in kind of how it converges in practice? And can you maybe say something about, right, which types of sampling problems are hard and which sampling problems are easy? Are they harder than we think they are or easier than we think they are?
That's an excellent question. So I hope you heard the question, but it's about how these MH techniques work in practice. So for the particular time series models that I've shown, what I found is the resimulation MH algorithm, while it produces highly accurate models in terms of finding nuanced structure, the models are not necessarily concise or short. So MH can produce actually much longer programs than you would expect. And so there, I think one probably needs to impose additional structure on the PCFG to have probabilities exponentially decreasing with the size of the program so that you're maybe a little bit context sensitive and stopping the resimulation from just doing more and more branches, branching more and more. So that I think, at least for time series, is the most common example, which is MH produces accurate models, but you sometimes don't have control over how complicated they are. And simplifying those models, of course, is a very interesting problem in its own right. Yes, Leo.
For us, how restrictive is actually that condition that you have to have the largest eigenvalues more than one, and how does it apply to two examples that you gave from the left side and the right side of the 0.49 and the 0.51?
Yes. So in terms of being restrictive, I think, so the question is how restrictive is the condition on the eigenvalues which are needed for the PCFG to halt with probability 1. I think if we go back to, I don't know if I'll be able to go to this here, let's see. So if we go back to this PCFG that, or this grammar that I showed in the beginning, if you want to implement this as a probabilistic program, then you actually need to make sure that this, that condition holds. And for complicated grammars, that's just something you need to do. And with regard to the second question where I was showing the example, the one with 0.49 actually has an eigenvalues which are less than 1. The one with 0.51, because the branching factor is 2, so there's 2 recursive calls that are happening, even though the branching probability is just above half, you're creating much more computation at each step than you'll be able to recover or terminate. So yeah, that's a great question. Yeah, one in the back over there. Yeah.
So for someone who actually is interested in applications of, let's say, time series forecasting, what is the advantage of using like synthesis of the PCFG PCFGs compared to something like an autoregressive deep neural network?
Absolutely. So the question is, what are the advantages of using Bayesian synthesis in a PCFG versus deep neural networks? At least I personally don't know much about using neural networks for time series data. Maybe other people will be able to tell you more about that. But I know at least from the statistical literature, which is, or the machine learning literature, which use these baselines, even though they may be faster to run, they may need, I mean, these predictions here are not all that accurate, right? They're sort of roughly accurate. You may need a lot of hand tuning before you can get models that represent, whereby even though synthesis may be slower in terms of runtime code, it's actually much less work for the practitioner to use. I hope, at least. Yeah. A question in the front? No? Okay. Yes. Yep, in the center, in blue.
How sensitive, like, do you have a certain intuition for how sensitive the discovery of good structure is to having good parameters within that structure?
Yes. So the question is, how sensitive is the quality of the synthesized programs and the parameters that are used for the program? Is that correct?
Yeah, like if you had the right structure with the wrong parameters.
Absolutely. That's a good question. So if you have the right structure and the wrong parameters, do you get good results? And I think the answer is usually no. But by decomposing the inference problem, one into structure and one over parameters, which is in the PCFG I showed, which I went by pretty quickly, you can break down synthesis into alternating between MH on structure and then maybe doing some gradient or multivariate gradients over the parameters, which for a particular structure, you can very efficiently get parameters which are probably best representative for that structure.
Each time you look at a structure, you assume you have maximum likelihood or the best parameters?
You would hope so, yeah. That would give you the most representative quality assessment of that structure. Yeah. Alexi.
So there's a perfectly good dynamic programming algorithm for taking a PCFG and generating the strings in decreasing probability order or something. Have you looked at using an A-star style search to get some top 90% of the posterior?
This is a very interesting question. I haven't, but we should talk more about that idea. Yeah.
Does that work with MH?
How does that work with MH?
Yeah, so the counter question is, right, if you can do this with a star style search, can you also do MH updates in the proposal?
Let's talk about that.
Yeah. It's a very, very interesting question. Hadn't occurred to me. I think there was one question. Yes.
Yeah, I had one more. In your linear regression over there, what kind of features you use? Because somebody can claim that, in your Bayesian model, you put a lot of, domain knowledge. But, there's certainly a lot of features you can encode, like, some seasonality features and stuff like that.
Mm.
What kind of features did you use for linear regression?
So linear regression is basically the simplest model you could imagine implementing, where you're only regressing on, so you're treating this as points in the XY plane, which is something people do, right? But the ARIMA baseline actually does encode seasonality, right? So it's using autoregressive integrating moving averages. And you can incorporate seasonality here. I think it's, what, four cycles per year or something. And the Facebook profit algorithm also has its own form of structure discovery, looking over those things. Yeah, yeah.
All right.
All right.
For all those questions, let's thank the speaker
Thank you,
again.
thank you.